Hello everyone, today we'll talk about the solution to the problem find the longest substring containing vowels in even counts. I think this is quite a tricky problem, so don't worry if you didn't manage to solve it by yourself. First I'll talk about the approach that works and then maybe about some other ideas when you look at that type of problem that don't work in this case. So one thing that we can do when you have a situation like this, so let's say that there are some letters that we do not care about, some letters that we do care about, so maybe an X, a B, an X, an A. So X is just a letter that we don't care about, which can be literally X in this problem. And one thing that we can usually do is to know the number of times a given letter appears in any substring of this original string. So for instance, how many times the letter B or letter C or letter A appears here. This is using standard prefix sums. That's because we can count the number of times that letter appears on the prefix up to the end of our subarray and subtract the number of times it appears on the prefix up to before the start of our subarray. And in this case, since we care about only the parity of the number of occurrences, then we can simply remember if the number of occurrences was odd or even. So essentially XOR it with 1, flip it from 0 to 1 or 1 to 0 whenever we encounter the letter. That's because calculating those prefix sums or prefix XORs is very simple. When we have a new value that changes the sum or XOR, we just take the previous value that we have calculated, XOR it with the new value, and that is the value for the next prefix. But this standard technique is not all that's needed to solve this problem. Another thing that's necessary is to, of course, combine it to a solution. That's because what we want is we want all those letters to appear an even number of times. And we cannot, even if we, or at least I don't know how we could, by using this array and even pre-calculating some things about this array, maybe look at a given position and then find the furthest away end that's good. So for instance, we can start and then try to get the, for instance, we start at an A, so we get the next A. And in that case, maybe some other letters, now this B, are wrong, so then we find another B. Now A's are okay, B's are okay, and now we're happy, but maybe we can get something longer. So I don't know if there is a solution that uses those situations like this, those pre-calculated sums like this. And the most natural way maybe of working with those vowels and the fact that both of them or all of them have to appear an even number of times is to consider every possible state a given subarray can be in. Because that subarray for A, E, I, O, U can be either have an even number or an odd number of occurrences. And that means that we want, if, for instance, if we are at a given position and our prefix, so for instance, our prefix here has an odd number of A's, odd number of B's, even number of, or, well, and of course here I use B as an example, of course that B should be a vowel, but that's why I'm using also a color here. So it has, of the interesting letters, an odd count of 1 and the other one of them. And now if we have to create a good subarray, then we have to find a prefix such that what remains is a good subarray, so something that will have an even number of occurrences for every vowel. So that means that the prefix that we found must have exactly an odd number of occurrences for the vowels that we have an odd number of occurrences, because then the subtraction gives us an even number, and an even number wherever we have an even number. So in other words, we have to find a prefix that exactly matches the state that our current prefix is in. And so that just means that if the number of states is not too crazy, or even if it is crazy, that's because the number of prefixes is not crazy, we can just calculate the current state. And of course, updating the state is very easy, because if we have a state for the previous prefix, then we get the next letter. If that letter is not a vowel, as in this case, we don't do anything. Otherwise, we have to flip the bit in our state corresponding to that vowel. So we had an odd number of A's, and now here we have an even number of A's, and here we have an even number of A's and B's, which B should be a vowel. And so in that case, we can just remember the first occurrence of any prefix which has exactly the same state as we do. And of course, there is also here an empty prefix that has the state of 0, everything is even. And that corresponds to the longest subarray, longest substring, being exactly a prefix of a string. And that leads us to a solution that should be very easy to implement. We remember the current mask. We remember that in a dictionary, for every state, the previous time we've seen it. And of course, the previous time we've seen 0 is at position -1. This is this empty portion of the string. And we remember the result. And now we go through all the letters in S. We can just enumerate it if it's a string. By enumerating it, of course, we also get the index. So we can just iterate over it. With enumerate, we get both the index and the value. Now, if that value is a vowel, then we have to flip the corresponding position in our state. Our state is a bit mask, and to flip a bit in the bit mask, you just have to XOR it. How do you XOR? So how do you flip the ix, so this index, bit at that position? You have to start with 1, which is bit at position 0, and shift it to the left by the number of positions you want to have to the left of 0. And of course, number of positions is just well, that's one way of doing it, is just all the letters in the alphabet we number from 0, so lowercase a is 0, and we just get the corresponding position of the vowel, and we flip it in the flag. So our flag will only care about positions of vowels. And now, if we've seen the exact same flag, the exact same state before, that might be a result. So the prefix that we're currently at position I, minus the position of the previous prefix that had exactly the same value, might be a result, so we max it with the result. And of course, if this is the first time that we see the given state, we remember it in our dictionary. So we only have to remember a state once, because we always care about the smallest prefix that has this state, because we want the longest subarray. And at the end, we can return the result. So this is this standard approach, this standard idea, that we can remember the number of times, or the parity of the number of times every letter appears in every prefix, and in that case, we can calculate that parity for every substring. However, we can do it in this problem. We have to combine all those information together, and this is one way of doing that, by just remembering the last time the thing that we would have to subtract from our current prefix to get a good prefix appeared. And this is often useful in different problems. And of course, I also mentioned that there are other approaches that you can have to a problem like this, and in this case, those approaches will not work. One idea, often when you have letters, then if you, let's say, start at some position and you want to push the right end forward some number of times to find the longest end for that beginning, then one thing that's often useful is to create for every letter, or for every vowel in this case, the positions of that vowel. So maybe this is at position 3 and position 7, this is at position 9, this is at position 4 and position 6. And an array like this has the same size as the original array, or at least it's not bigger, but it allows us to both binary search in all of those subarrays to find the next occurrence that's smaller or bigger than some value. And also, if we iterate through that array, we can just iterate over all the a's based on their positions. But it will not work in our problem, even combined with the original idea of remembering the number of times every letter appeared in a prefix. That's because we want all the vowels to appear an even number of times. So maybe if we have an odd number of a's, okay, so we jump to the next a. That's fine, but now maybe some other letters have an odd number of occurrences, so we have to update it. That should be easy. But then we have to jump again, and again, and that will probably lead us to a quadratic solution. And this solution is, of course, linear.